Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah walhamdulillah wa salatu wa salamu ala rasulillah amma ba'd. So this lab deals with the timers. Timers are simply registers inside the microcontroller which can keep on counting on their own. In PIC18 microcontrollers, in PIC18 F4580 microcontroller, we have 4 timers: timer 0, timer 1, timer 2, and timer 3. So these are simply a collection of registers which can keep on incrementing on their own. So this is the timer 0 module inside PIC18 F4580 microcontroller, and you can see the timer 0 control register given here. Then we have timer 1 module, timer 2 module, and timer 3 module. So each of these timer modules, they have these registers, as you see here, TMR3H and TMR3L. Similarly, here we have TMR2 register, and here we have TMR1 H and L register, TMR0 H and L registers. So these are the registers which can keep on incrementing. So these are the 2 registers which can keep on incrementing on their own in the background. So previously, when we used delay loop, we defined 2 counter registers, counter high and counter low, and we increment those counters inside the delay subroutine by using decrement file register decrement instruction of the increment instruction. But in the case of the timers, we don't have to manually increment the timer. It keeps on incrementing in the background. Once we enable it, once we set up the timer properly, they can keep on incrementing. So these registers, they start from 0 and they keep on counting, and they will keep on counting until they reach their maximum limit, which is FF. So for 2-bit registers, it is FF, and for 16-bit registers, for 2 registers together, it will be FF, which corresponds to 65535. So this block diagram, it shows you how a timer increments. So when we set up the timer, it keeps on incrementing on every instruction cycle. So we have the oscillator frequency, for example, 8 megahertz. So every instruction cycle is divided by 4. So 8 megahertz divided by 4, we get 2 megahertz. And at every 0.5 microsecond, which corresponds to 2 megahertz oscillator instruction cycle frequency. So at every half microsecond, the timer register increments on its own. And the timer, this is the default operation for the timer. It can keep on incrementing on every instruction cycle. So it starts incrementing from 0 until it reaches FFFF, which is 65535. So the total time taken for this timer to complete its one cycle from 0 to FFFF will be 65535 multiplied with 0.5 microsecond. Similarly, if the clock frequency is 4 megahertz, then each instruction cycle frequency will be 1 megahertz, which corresponds to 1 microsecond, and the time taken for the timer to complete its complete cycle or its complete count will be 65535 microsecond. Now the timers, when they complete their cycle, they generate an interrupt. As soon as it reaches its maximum limit, they generate an interrupt, and it is known as the timer interrupt. So here the example is given for timer 1 interrupt, and as you see in the block diagram here, as soon as the timer completes its cycle, timer 1 IF bit will be set as 1. So this will indicate to the user that the timer has completed its count. So we can use timer in 2 different modes: to keep track of time and to count some pulses or to count some signals. So if you want to keep track of time, then the timer is uh, configured to increment based on the internal clock cycle of the instruction cycle of the microcontroller. So let us look at time 1 control register. This is the 0 con. So the first bit here, or bit number 7 here, is the enable bit. So when this bit is 1, it enables the timer, it starts the timer. And the next bit here is the timer 0 8-bit. So timer 0 can work in either 8-bit mode or 16-bit mode. So in 16-bit mode, it uses both the registers, timer 0, high and low byte. And in 8-bit mode, it will only use the low byte, timer 0 L register. So if you want to use timer 0 in 16-bit mode, then this bit should be 0. So by default, this bit is 1. That means timer 0 will run as an 8-bit timer as default. If you want to make it a 16-bit timer, then this bit should be 0. So by default, the timer can be configured to increment on every instruction cycle. So if we have, for example, if we have 4 megahertz as the clock frequency, then the time taken to execute one instruction is 1 microsecond, and for the timer to count from 0 to 65535, we get 65,536 microseconds. So this is the calculation for finding out how much time is taken for the timer to complete its cycle. 1 divided by 1 megahertz, which is the oscillator frequency divided by 4, multiplied with the number of steps for the timer. So the number of steps for the timer in this case for a 16-bit timer is 65535, 0 to 65535, which is 65,536 for a 16-bit timer. For 8-bit timer, we simply multiply with 256. So this is without using a prescaler. So we see here in the timer 0 control register, the last 3 bits are the prescaler select bit. That means we can choose one of these options from here to slow down the timer. So instead of incrementing on every instruction cycle, the timer can be configured to increment on 2 instruction cycles, or 4 instruction cycles, or 8 instruction cycles, depending on the selection that we can choose from here. So for example, if we choose the prescaler as 2, then instead of counting on every instruction cycle, the timer will increment on 2 cycles. The timer will increment once on 2 cycles. So if we, for example, if we select the option 64 here, then after every 64 instruction cycles, the timer will increment by 1. So the total time taken for the timer to complete its count will be multiplied with the prescaler. So here in this case, in this example, in the calculation given here, we are simply multiplying 1 microsecond, which is for 4 megahertz oscillator frequency, which we are simply multiplying 1 microsecond with the timer count. So this is the timer count, and if we use a prescaler of 64, then we must multiply this with 64 to get the total time. So after completing its cycle, when the timer completes its count and it reaches FFFF, it will overflow. That means it goes back to 0 again. So when the timer overflows, it generates an interrupt. So this bit, the timer 0 interrupt flag bit, or if you're using timer 1, then timer 1 IF bit, that bit will be set as 1 when the timer overflows. It goes from the maximum count to 0 again. So the time taken from the start of the timer until it overflows depends on the clock frequency, and it depends on the prescaler selection. So if we choose a prescaler from here, we have to multiply that in the equation to get the number. We have to multiply that with the number of steps of the timer to get the total time taken for the timer to overflow. So here is another equation given, a simplified equation. You can see time taken in seconds equal prescaler multiplied with the timer steps. So what the number of steps taken by the timer multiplied with 4 divided by the oscillator frequency. So we can use a timer instead of a delay subroutine to add a delay or to keep track of time in a microcontroller. So suppose you want to generate an interrupt after every 60 milliseconds. So 65535 or 65536 is 65.5 millisecond. So suppose if you want to generate an interrupt after exactly 60 millisecond, so in that case what we can do is we can preload the timer registers. We can preload these registers, the timer 0 or timer 1 low and high byte registers with an initial value. So because the timer always increments, it does not decrement, so we can preload these two registers with an initial value and let the timer increment from that number until the limit, which is 65535. So using that, we can control after how many microsecond or after how many millisecond the timer should generate an interrupt. So in the example, if we want to generate an interrupt after exactly 60 millisecond, so what we do is we simply subtract from the maximum limit. So our maximum limit is 65535. We subtract from there 60,000. So if we subtract 60,000 from 65535, we are left remaining with 5,535. So we can load the timer registers with 5535 as the initial count. So if we convert 5535 in the hex format, so 5535 in the hex format it is 15 9F. So we can load 9F in the low byte and 15 in the high byte in the hex format, and let the timer count or let the timer increment from this number until the maximum limit, which is 65535, which is FFFF. So by doing that, what we are doing is we are simply reducing the timer steps. So instead of letting the timer count from 0 to FFFF, we are letting the timer count from 15 9F to FFFF, and we get exactly 60,000 number of steps. So here we have the timer 0, low byte and high byte, and we load them with this initial value 15F, 15 and 9F. As we have just calculated. So if we load these two registers, timer 0 high byte and low byte with 15 and 9F, and let them count from here until FFFF, then we have exactly 60,000 steps. So when we have exactly 60,000 steps, then the time taken for the timer to overflow, or the time taken for the timer to generate an interrupt, will be exactly 60,000 microseconds, which is equal to 60 millisecond. So this way you can control the time taken for the timer to overflow or to generate an interrupt. Similarly, in another example, if you want the timer to generate an interrupt, if you want the timer to generate an interrupt after 3 seconds, so 60 millisecond is the time taken for the timer to generate an interrupt without a prescaler. So if you want the timer to generate an interrupt after 3 seconds, then we should increase or we should add a prescaler. So what prescaler should be chosen from here? So we have these options here. If you want to assign a prescaler, then we select we select the prescaler bits from here, and the next bit here is the prescaler assignment bit. The prescaler assignment bit indicates whether the prescaler is assigned to the timer or not assigned. So here we don't see an option for the timer to increment on every instruction cycle. The prescaler starts with 1:2, then you have 4, 8, 16, 32, 64, 128, and 256. But what if you want the timer to increment on every instruction cycle? So in this case, we do not assign the prescaler by using the PSA bit. So PSA bit is the prescaler assignment bit. If it is 1, then the prescaler is not assigned and the timer will increment on every instruction cycle. And if it is 0, then the prescaler is assigned and it will take one of these prescalers into account, and you have to add the prescaler in the equation. Now suppose in the other example, if you want the timer to generate an interrupt after 3 seconds. So 3 seconds is greater than 65 milliseconds. So in this case, you must use a prescaler. So let us find out how much time will be taken if we use the prescaler 1:2. So this will be simply multiply this by 2, then you get 128. So let's multiply this by 2. Okay, so you get 131 millisecond. So you get the total time taken for the timer to generate an interrupt will be 131 millisecond. So if you choose a prescaler of 4, so once again let's multiply this by 4. So it will be double of that, and you get 262 millisecond. So 262 millisecond, is it greater than 3 seconds? No, it's again less than 3 seconds. It's in fact less than 1 second. So we have to keep on adding the prescaler. So if we keep on adding the prescaler, the time taken for the timer to generate an interrupt will keep on increasing. So let us say if we choose a prescaler of 32, then what do we get here? 65535 multiplied with 32. Okay, so we can see if we choose a prescaler of 32, then we can get a 2-second delay. If we choose a prescaler of 32 with 4 megahertz clock cycle, which gives you 1 microsecond for each instruction cycle. So the time taken for the timer to generate an interrupt with a 32 prescaler will be 2 seconds. So if we need a 3-second, exactly a 3-second time for the timer to generate an interrupt, then we must choose a prescaler greater than 3 seconds. So once again, let's go to the next step and choose a prescaler of 64. 65535 multiplied with 64. Now this gives us 4.194 second delay. If we choose a prescaler of 64 with 4 megahertz oscillator frequency, then the timer can generate an interrupt on 4.194 seconds. So now this is greater than 3 seconds. So what we do is we subtract from this 3 seconds minus 3 seconds will be simply 3 million microseconds. So we subtract that number from here. Okay, so we get this number. Now in this number we divide this number by 64. We divide this number by the prescaler. So just divide this by 64. Okay, now we get this number. We get 18,660. In hex it is 48E4. So what we do is we load this number as the initial value in the timer registers. So for example here, so if we load the timer registers with an initial value of 48E4 as we see here, then the total number of steps that we have is 46,875 steps from 48E4 until FFFF. If you multiply these steps with 64, then we get exactly 3 seconds, or exactly 3 million as the number, which corresponds to 3 seconds. And in each second, based on our calculation, if the oscillator frequency is 4 megahertz, instruction cycle frequency will be 1 megahertz, and the time taken for each instruction cycle will be 1 microsecond. So the total time taken for the timer to generate an interrupt will be exactly 3 seconds. So this is how we can choose a prescaler and calculate what should be the initial value. So this is how we can calculate the initial value to load the timer registers with an initial value to generate an interrupt after a predefined time or after our desired time. So this was all related to the timer prescalers and the amount of time taken for the timer to generate an interrupt. Now the remaining 2 bits here. So we have seen bit number 7, which is timer on bit, bit number 6, which is timer 0, 8-bit selection bit. If it is 1, the timer is configured as an 8-bit timer. If it is 0, the timer is configured as a 16-bit timer. And we have seen the prescaler bits and the PSA bit, prescaler assignment bit. Now we have 2 more bits left here. The timer 0 clock source select bit. So until now we have seen incrementing the timer based on the instruction clock cycle or the instruction cycle. Now if we want the timer to count external pulses, so the timer can also be configured to work as a counter. So in the counter mode, the timer can count external pulses on timer 0 clock pin or timer 1 clock pin, depending on the selection of the timer. So if we set this bit as 1, so it will count transitions on this pin, the timer 0 clock pin. If you look at the pin diagram, we'll find there is a pin known as timer 0 clock pin, this pin in the diagram that we use for 40 pin microcontroller. So this is the pin, timer 0 clock pin. We can connect an external signal, or we can connect an external source like a sensor or a push button. We can connect on this pin and let the timer count the transitions on this pin. So this is for the timer 0, and for timer 1 we have timer 1 clock pin. So timer 1 and 3, timer 1 and timer 3, both of them, they have the same clock pin. So if we select this pin, if we select timer 1, then the timer 1 in counter mode or timer 3 in counter mode, they can count pulses on this pin, T13 clock pin. So the pulses can be either a rising pulse or a falling pulse. The transitions can be a high to low transition or a low to high transition. So we can use this bit timer 0 source edge select bit to let the timer count either on high to low transition or on low to high transition. So we have examples of using the timer in counter mode by counting external pulses. So let's look at this example. So in this example, we have this push button connected on timer 0 clock pin, and we have an LCD connected on the output. So the most basic example which everyone knows is the digital tasbih counter. Digital tasbih counter, which you can wear on your finger. It has two buttons. One is the counting button, other is the reset button. So what happens is when you press on this button, it keeps on incrementing the count. It simply keeps on incrementing the count. And if you want to reset, you can press on the other button to reset the count. So we have a simulation of the similar connection. So we have this button which can keep on counting, and we can also connect a reset button if you want on one of the other pins of the microcontroller. And you have an LCD connected here to the microcontroller. So when you press the button, there is a transition. So now by default on this pin, on pin number 6, timer 0 clock pin, the input is 1. You can see the red dot here, which indicates the input is 1 because it is connected to high volt. It is connected to 5 volts. Now, when you press the button, there is a transition. There is a high to low transition. There is a high to low transition, and when you release the button, there is a low to high transition. So as soon as there is a low to high transition, the timer is incrementing by 1. The timer is incrementing by 1, and you can see the count is incremented here on the LCD. So when you press it again, you can find there is a high to low transition, there is no increment, and when you release the button, there is a low to high transition, and you can see the timer is incremented and the count is incremented here. So you can keep on pressing the button and you can keep on counting. So this is how we can design this is how we can design a digital counter by using a button. And in this case, since we have a low to high transition counting, so this bit will be 0, bit number 4, this bit will be 0, bit number 4 will be 0. We have to enable the timer. We have to configure the timer as an 8-bit counter or a 16-bit counter, and then this bit must be set as 1. So if this bit is 1, it will count transitions on this pin, timer 0 clock pin, and this bit, depending on the transition that you want, either high to low or low to high, and the prescaler. So in our example, in this example, we want to count every button press. So in this example, we want to count every button press. So we do not select the prescaler. We do not assign a prescaler. Now let's look at some other examples as well. So this is one example. Now the timer can also be used to measure the RPM of a motor. The RPM of the motor can be measured using many different methods. One of the method is by using, for a DC motor, one of the methods is by using a Hall effect sensor. So in this example, you have 3 Hall effect sensors connected here. You can see here H1, this is one Hall effect sensor, this is another sensor, this is another sensor. So in a DC motor, you have magnets and you have magnetic coils. So when the motor rotates, the Hall effect sensor is simply a magnetic sensor. So when the motor rotates, the polarity of the magnets on these coils, it keeps on changing. So as soon when it keeps on changing, you can see in the animation here, when it keeps on changing, the signal on these Hall effect sensors, they keep on changing from high to low, because Hall effect sensors are simply magnetic sensors. So they detect the magnetic field, and when there is a change in the polarity between North Pole and South Pole, you can see the signals on these Hall effect sensors, they keep on changing. So by calculating the number of pulses that we get in 1 second, we can calculate the RPM of the motor. And these Hall effect sensors, they can also be used as positional indicators. So they can indicate the position of the shaft of the motor. So this is another application of using the timer in counter mode. So the output of these sensors, the output of these Hall effect sensors can be connected to the timer 0 clock pin. So it can be connected to the timer 0 clock pin, and we can select a prescaler depending on the number of coils inside the magnet. So in one rotation, in this example we have 2 magnets. So in one complete rotation, you can get 2 pulses. Different DC motors have different number of coils. So some of the DC motors, they have 64 coils, some of them they have 8 coils. So depending on the number of coils you have in your DC motor, you can select a prescaler. So that prescaler will indicate on how many signal changes the counter should increment by 1. So if you have, for example, if you have 8 coils inside the DC motor and you are using if you are using the Hall effect sensor, then select the prescaler 1:8 and select 1 here on this pin, timer 0 clock pin, and it will keep on counting signals on 8 pulses. So it will keep on incrementing on 8 pulses. So in this case, you have to measure the RPM with respect to time. So RPM stands for rotations per minute. So you have to measure the RPM with respect to the time. So you'll need two timers here. One timer will be configured as a counter. One timer can be configured as a counter which counts transitions on the external pin, and another timer to keep track of time. So after every 1 minute, you have to see how many pulses you have in 1 minute, and you can indicate that as the total as the RPM of the motor. So RPM stands for rotations per minute. So what we have to do is we have to configure two timers. One timer 1 for example, can be configured in timer mode to generate an interrupt on 1 minute, and timer 0 configured in counter mode to count transitions on timer 0 clock pin. So it will count transitions based on the Prescaler selection. So if you choose for a motor with 8 coils, 8 magnetic coils inside, you will get 8 pulses in one rotation with one Hall effect sensor. So you have to choose a prescaler of 8. So timer 0 configured in counter mode counts the transition, it keeps on incrementing, and after 1 minute, when timer 1 generates an interrupt, so in this case after 1 minute you take the count from the timer 0 counter registers and display them on the LCD, and this will be displayed as rotations per minute. But in this case, in this example, when we start our measurement, we'll have to wait for 1 minute to get the result. So instead of that, we cannot wait for 1 minute. 1 minute is too long for 1 minute is too long for a person to get the result. So instead of waiting for 1 minute, what we can do is we simply divide this 1 minute by, we scale down and we divide this 1 minute by 10 or by 100, for example. So 1 minute is 60 seconds. So instead of 60 seconds, we can get an input after 6 seconds or after 600 milliseconds or even after 6 milliseconds. So instead of getting instead of taking the reading from timer registers after 1 minute, we simply change this and let us say after 6 seconds or after 600 milliseconds. You can get the reading from timer 0 register, from timer 0 high and low band, and display it on the LCD as RPM divided by 100 or RPM divided by 1000. So in your car, usually you find a tachometer which indicates the RPM of your engine, and these numbers they start with 0, 1, 2, 3, 4, 5, and you can see at the bottom you will find multiplied with 1000. So what happens is when you place your foot on the pedal, the RPM of the engine, it keeps on increasing, and you cannot wait for 1 minute to get the feedback from your car. So instead of that, inside the car, this RPM measurement is divided by 1000. So instead of getting an input from the sensors of the engine after 60 seconds, they divide the 60 seconds by 1000 and you get a reading on every 60 millisecond. So on every 60 millisecond, the feedback from the engine is shown to the user or to the driver on his dashboard. So this is another method of using or measuring the RPM of a motor using the timers and using a Hall effect sensor. And there is a third method by using an optical disc. So if you have a rotating motor, you can connect a slotted disc on the shaft of the motor, and you have an optical interrupter, you have an LED you have an infrared LED, and you have a light detector. So what happens is when the disk rotates uh, and the light passes from one of these slots, so a pulse is generated. A pulse is generated, and that you can count the number of pulses, and once again you can divide them by the prescaler for the number of slots given on the disk. So if suppose for example here if you have 128 slots on this disk, then you can choose a prescaler of 128, and after 128 pulses the timer will increment by 1, and that way you can measure how many rotations of the disk has taken place, or how many rotations of the motor has taken place. So this is another method of measuring the RPM of a motor using timers. So here in this example, in this block diagram, you can see the timer is configured in the timer mode, and it is counting pulses based on the prescaler. It is counting pulses depending on the oscillator frequency divided by 4, and here you have the timer source select clock select bit. So if this is 0, it is counting internal clock cycle divided by 4 and multiplied with the prescaler, and the timer registers are incremented, and when they increment to the maximum limit, which is FFFF, they generate an interrupt, and the timer flag bit will be set as 1. And there is another example in the counter mode. So in the counter mode, here the timer is counting external transitions on this timer 1 clock pin or timer 0 clock pin depending on the selection of the timer, and you can select whether the timer should count on the rising edge or the falling edge, depending once again depending on the prescaler. The timer registers will keep on incrementing until they reach the maximum limit. So these are the two applications of the timer and two mode of operations of the timer, timer mode and counter mode. And once again in the timer mode, if you want the timer to generate an interrupt after a predefined or after a particular time, then you must load the timers with an initial value as we have seen here before. So if we load the timer with an initial value, if we load the timer registers with an initial value of 159F with 1 microsecond time take 1 microsecond for each increment, then we have exactly 60,000 steps, and the time taken for the timer to generate an interrupt will be 60 milliseconds. And in the other example that we have seen is if we want to use a prescaler, if you want the timer to generate an interrupt, if you want the time to be greater than 65 milliseconds, and the example given here was for 3 seconds. So if you want the timer to generate an interrupt after 3 seconds, then we have to use a prescaler to slow down the timer. So if you use a prescaler of 1:2, so 65535 multiplied by 2, we get the time as 131 millisecond for the timer to generate an interrupt. Similarly, with a prescaler of 8, we get 524 millisecond for the timer to generate an interrupt. And similarly, in this way, we kept on increasing the prescaler until we got 4 seconds, which is greater than our required time. Our required time here in this example was 3 seconds. So we got 4 seconds here with a prescaler of 64. So we choose this prescaler, we choose the prescaler of 64, and then we subtract the time that we need. So we get 4 seconds. We get 4 seconds with the 64 prescaler. So we subtract from this 3 seconds this way. So we get 1194240, and then we divide this number by the prescaler, which was 64, and we got 18660. So 18660 is the initial value. 18660 is the initial value that we should load in timer 0 and timer 0 low and high byte to get exactly 46,865 steps. So now if we 65535 minus we get 46,875. So this is the number of steps. So let's calculate again. These are the number of steps. Multiply them with 64 and we get exactly 3,000. We get exactly 3 million microseconds, which is exactly 3 seconds. So this is how we can use the timer in timer mode and counter mode. These are the steps given here for using the timer in timer mode and counter mode for measuring time and to count pulses. And in the activity, we have to calculate the RPM of this motor. We have to calculate the RPM of this motor connected on timer 1 clock pin and display the RPM on the LCD. So we are dividing the RPM by 100. So on every 600 millisecond, we take the count and we display it on the LCD. And since I have connected an oscilloscope here, you can see the pulses here. You can see the pulses on the oscilloscope. So the template for writing this program is given to you, and it makes it very easy for you. So timer 0 should be configured to generate an interrupt on every 600 milliseconds. So follow these steps and complete the program. So configure 8 megahertz internal oscillator and configure timer 1 clock pin as input pin. Initialize the LCD, clear the LCD display. Configure timer 0 to generate an interrupt on 600 millisecond. Using a prescaler, calculate the prescaler, whatever prescaler you need. So 600 millisecond is greater than 65535. So you need a prescaler. So calculate the prescaler and timer 1 to count external pulses with 1:2 prescaler. Here it's given as 1:2 prescaler because in the lab on the mechatronic demo board we have a DC motor, and that DC motor has 2 slots. So we have seen an example here with a slotted disc. So that DC motor on the mechatronic demo board in the lab, it has 2 slots, only 2 slots. So in one complete rotation, you get 2 pulses. So in one complete rotation, you get 2 pulses, and we can use a prescaler 1:2 to calculate one complete rotation. So by completing this, you can complete the activity of lab 7. And before the activity, you have a homework, lab homework 6, which is read the chapter on timers given here on this link. It is the same chapter which I have explained from where I have explained to you. So read this chapter completely, and it will explain you the working of the timers in detail. So this is based on PIC18 microcontroller. So you'll find small differences here. For example, here the PSA bit is used to either assign the prescaler to the timer or to assign the prescaler to the washed-out timer instead of simply not assigning the prescaler. So you'll find small differences between PIC18 and PIC18 microcontrollers, but other than that, the function of the timer and the configuration of the timer and the working of the timer explained here in this chapter is exactly the same as it works in PIC18 microcontroller. So this is all we have for lab 7 for this lab. والسلام عليكم وآخر دعوانا الحمد لله رب العالمين سبحان الله وبحمده سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.